Alright, in this video I want to determine the roots of an equation with real coefficients. So this is a question where we've got once again a complex polynomial, but the coefficients of this polynomial are a special situation where each one of the coefficients is a real number, and we use a special conjugate root theorem to solve it. Okay, so we can only use this conjugate root theorem when we have real coefficients on each one of the terms in our polynomial. So let's have a look at the question first of all. It says negative 3 plus 2i is a root of the cubic equation 2z cubed plus 9z squared plus 8z minus 39 equals 0. Determine the other two roots by expressing the equation in the factorized form. Okay, like I mentioned earlier, the conjugate root theorem is what we're going to use to solve this, and it says that for polynomials with real coefficients, okay, so that's important, they all have to have real coefficients. The complex roots, when we have p of z equals 0, they occur in conjugate pairs. So a conjugate, remember, that is, if we have a z equals something, then z bar is its conjugate. Alright, let's just see what we've got here. So what we're saying is negative 3 plus 2i is a root, therefore z equals negative 3 plus 2i, because negative 3 plus 2i is a root, and z bar is its conjugate equals negative 3 minus 2i. So all you do for conjugate is you just change that sign in the middle there. Okay, and immediately we've solved part of this problem because it says find all the roots. Okay, and here we've just solved by using this theorem. This is the second root. This is one, this is the first one, this is the second one. Okay, so we've immediately got two roots. How do we write that as a factor? We take the negative 3 plus 2i, or the negative 3 minus 2i, to the other side of the equal sign. Therefore z take negative 3 plus 2i, I'm just going to write it as a bracket here. That's a factor multiplied by, I'm not going to write z bar, it's just z as well. Take negative 3 minus 2i, that's another factor. And because this is a cubic polynomial, I know that there must be one more factor at least. So I'm just going to write it. I don't know what that is. This is what I'm trying to solve now, my third factor. So I'm going to say a of z plus b, because I know that's the form that it has to be in. And I'm going to try and solve for a and b in this. Okay. What I also know is that this factor times the second factor times the third factor must equal my polynomial, which is 2z cubed plus 9z squared plus 8z minus 39. Okay, so like I did in the previous example, when we have this kind of layout, we can say the first here times the first in the second bracket times the first in the third bracket should give me this first term of my polynomial, as long as the polynomial is in descending order. Okay, so from z cubed to z to the power of 0 there. So what I'm saying is, therefore z times z times az, because we don't know what a is yet, equals 2z cubed. Okay, you can see quite easily, therefore a equals 2. That's the first part of the puzzle. So we've got a solved out of this last factor. We still need to find b. B is the last in the bracket, so just like we did with the z, we're looking at, this is the whole second part of this term. Okay, so this is the second part of the term, this is the second part of the term, and last times the last times the last must give me this last piece as well. So that's what I want to do for this piece now. So I'm going to say therefore negative 3 plus 2i. You're probably wondering why am I carrying this negative along here with me? Remember, when we write a factor, it is in this form. It is az plus b. So because this has got a negative sign in here, I'm going to carry that out. Okay. So negative 3 plus 2i times, you can put a bracket around that if you like for neatness, times negative 3 minus 2i times the last one, which is b, would equal negative 39. Okay, so I took the second half here times this second half there times this second half there, and that should equal my last term of my polynomial. So let me neaten this out here. What have I got? Therefore 3 minus 2i, so I'm just multiplying that negative through, times 3 plus 2i, so you can see there's a difference of 2 squares there, times b equals negative 39. Therefore, so 3 times 3 times 3, there's 9, and then I know that the middle term is going to fall away, so I'm not going to multiply that out. So it's 3 times 2i, 6i, negative 6i, so that middle term falls away, minus 4i squared. So keep in mind, we said I squared equals negative 1, and we're going to use that in a bit. Okay, so that times b equals negative 39. Therefore 9 minus 4 times negative 1 is plus 4. 9 plus 4, b equals negative 39. Therefore 13b equals negative 39. Therefore b equals negative 3. So we solved for a. A was equal to 2. That was nice and simple. This one was a little bit trickier, but we got there in the end. B equals negative 3. So let's just put it together now. That factor was written as az plus b is equal to 2z minus 3. Okay, so this is the other factor that is the third factor, and we can write it out in factorized form. Therefore, let's put them all together. So we've got z take 3 minus 2i z take negative 3 plus 2i and 2z minus 3 of the 3 factors. If I wanted to know what the roots were, we could say that these are the roots here. So like I've said earlier, these are the roots. Okay, let's try just explore what this root would be, even though the question doesn't ask us to do that. So the roots would be negative 3 plus 2i, negative 3 minus 3i, and for the last one, this would be, think about this one here, we're saying basically that 2z equals 3, therefore z equals 3 on 2. So this is a real root, okay, and that's what the conjugate root theorem states, that it could be, the third one could be a purely real root, okay, and that's what this example has, but it could also be an imaginary part there. So hope that example made sense, and I'll see you in the next video.